All right. This is almost like making a movie where it's like, ah, okay, cut, take two. So we're just going to basically say everything that we just said, including my welcome to you and thank you for being here, which easy for me to repeat that because it's very much true. And I really, really do appreciate you being here. So we are starting off this morning with this discussion of the AI engine ML version 2. And we want to discuss how this is different, how this is updated, and also give you a sense of where this is headed. Like, what's the trend? What is AMD doing with regard to the AIE technology? How this fits into the broader Versal platform and what you can expect as we move forward. So we're going to specifically focus on the architecture of the AIE ML version 2. And ML stands specifically for machine learning. And one of the things that you can immediately glean from that is that although you could use the original AIE for machine learning, really wasn't as optimized for that. It was more so for doing um, DSP type operations where you are handling graphics data, you're handling images, and you're doing filters and fur filters and FFTs and things like that. So this is more optimized for that. And I'll show you exactly what that means as we get into the lecture. So when we come back to this slide, when you look at the upper right-hand corner, there's a couple of things I want you to think about as it relates to data processing and using these individual tiles in the SIMD data path. Let me get my cursor up and going. So this is what we're looking at. The AI engine tiles are arranged in a two-dimensional structure. And when you look at that, it might immediately seem like, okay, wait, well, this is like a GPU where I have individual compute elements. And yeah, it is similar to that, but it's actually more powerful than a standard GPU because what you're doing in this case, you're allowing each tile to actually do SIMD operations. The way SIMD operations gets done typically in a GPU is that you take your data and you organize it into sections and subsections. So if you're looking at like the OpenCL standard, and let's say you're processing graphics data, you pass in an 8 by 8 frame, and you're going to perform the same operation on each pixel in that frame. So rather than doing it sequentially, where you're going to do 8 by 8, 64 sequential operations to process that frame of data, instead, you organize it as individual 8-bit groups. And the way this works in OpenCL, you would consider those work items and work groups. And you would pass that in, and you would have different functional elements that are going to handle those individual 8-bit chunks of data. So that's basically what a GPU does. The AI engine tiles are a little bit more sophisticated than that because each tile can actually do its own parallel operation. And that's not something you can do with the standard GPU. Like you can't pass data into that and then have a SIMD path. The SIMD path is actually made up from the fact that you're using multiple individual processing elements to handle the work items and the work groups. Well, with this technology, a single tile handles the SIMD data path. I can be processing anywhere from 4 up to 8 lanes of data in a single tile. So what am I doing with all these other tiles? Well, it just gives me additional capacity. I can be doing multiple operations. I can be doing things in parallel. I can partition some functions across multiple tiles. So when does that become important? Let's take the example of a really, really high speed fur filter. And within a fur filter, you run up against two limitations, and both of these have to be effectively balanced. Your sample rate and then the number of taps, because for every sample, you're going to have to do that number of multiplications and accumulation. So if you have a higher sample rate, and if you also have a high number of taps, and that high number of taps is typically related to having a more quality filter, to having a better response, being able to do better signal processing overall. But you could get up to the point where this is too much processing thing that can be done on one tile. In which case, you now start looking at like a semi-parallel filter, maybe even a full parallel, but at least you would start with a semi-parallel. So let's take a simple example. Let's say I have a 32 tap filter, but I have a really, really high input sample rate. I could, rather than implementing the entire code on a single tile, I could break that up over two tiles. So I could have half of my coefficients on this tile and half of my coefficients on this tile. So that would mean I could support a much higher sample rate and still do the computation. Now, how is it physically working? Do I just feed data from one to the next? There are dedicated connections, not just from the tiles to the adjacent tiles and to the adjacent memory and to the streaming interfaces, but there are actually dedicated connections that feed the accumulator of one tile into the accumulator of another tile. So if you're thinking of a per filter, of course, your output is going to be a sum of products. So if I can take the accumulated value from this tile and feed that directly to the accumulated value in this tile, then I am basically gathering the sum of products. So all that to say that when you think about the AI engines, this is a really unique structure. It has flexibility, but because each tile can individually do parallel operations using the SIMD capabilities, this is really more powerful than a standard GPU. So you've got three different flavors of this, starting off with the original AIE, which is optimized for DSP and communication, then the AI Engine ML, optimized for machine learning, then the update to that, what we're calling V2, is also optimized for machine learning, but now they're doing what they call advanced machine learning workloads. That's a fancy way of saying that they can handle um, specific data types, floating point data types that would be particularly important if you're doing machine learning inference. So let's come back to this for just a moment. The original family was optimized for 32-bit data types. And what I mean by optimize is when you push data through that SIMD processing execution pipeline, that is 512 bits wide. And if you're doing 32-bit data, let's say you have 32-bit coefficients, maybe 16-bit sample data or 16-bit sample data and 32-bit coefficients. At any rate, you can do up to about 16 or 32 operations in a single clock cycle. So every clock cycle, and remember that the AI engine uses its own clock, similar to what happens with the NOC. It's using its own dedicated clock, which is generated through internal PLLs. You provide a single clock input to the Versal device, but it uses its own PLLs to create the clock for the AI engines, which is typically running at about 1.2 to 1.3 gigahertz. So when we talk about being optimized, we're saying that we can do more 32-bit operations in a single tile. But when you think about machine learning doesn't actually use 32-bit data types, not in an inference model. Whenever you're doing anything with machine learning, you have two very, very different, very, very distinct phases of development and deployment. The first is the training process. That requires 32-bit floating point data types. And that's where GPUs will have an inherent advantage over an FPGA. So the AMD approach and the Xilinx approach to this is to tell customers, okay, yeah, absolutely. Train your model on a GPU because otherwise you're never going to get closure. You're never going to get to the level of accuracy and convergence that you need. But once you achieve that, When you're ready to go to the field, when you're ready to deploy this, you don't really want 32-bit floating point data types, and you don't need that. If you try to take that to the field, that is going to be extremely costly in terms of resources and computational requirements, area, power, and everything else. So when we in, when we get to the deployment stage of what we call inference, we're actually going to convert those 32-bit floating point data types to 8-bit fixed types. And that's part of what happens in the Xilinx AMD design flow. You go into a tool called Vitis AI, which interfaces to whatever front-end framework tool you're using, like PyTorch or TensorFlow or Onyx, and it takes those outputs, the ones that you've already generated from the training process, and then it converts them. It converts them into 8-bit fixed types. Now, obviously, that means you're essentially truncating those values and now represent it as fixed point. So does that affect the accuracy? Yeah, slightly, but not as much as you might think. So you typically do just a little bit of training in the FPGA, not the original training, because that's impossible. You do a little bit of training to basically restore that maybe 1 or 2 degree of a percentage point of accuracy that happens when you translate this from a 32-bit to an 8-bit type. So again, what is it unique about this? They optimized the AI engines to be able to handle 8-bit data types. Because even though we could do it here, we could do upwards of about 128 per clock cycle. In the newer devices, in the ML versions, you can do anywhere from 256 all the way up to 512, depending on the relationship between the data and your coefficients. So in the case of a machine learning model, we're talking about the image data versus the weights and biases that are being used to multiply against that. So the AI engine ML does two really, really important things. One, it increases the number of 8-bit operations that can be done significantly, and they provide additional resources by putting memory at the very bottom of this. So we'll get to that here in just a moment. So then what's unique? When we get to Gen 2, you not only have the features and capabilities that we just discussed here, you not only have the enhancements to the technology, but there is now support for um, the block floating point data types, basically MX6, MX9, bfloat, as well as um, the float 16. And all of that is optimized again for machine learning, and it lets you take advantage of these newer, basically relatively advanced floating point data types, where MX6 and MX9 are what we call, again, block floating points, where you have a common exponent and then you have a different mantissa. But that allows more data to be processed, and you still have the advantage of floating point. Now, obviously, it is not 32-bit floating point data types. You don't have a 8-bit um, exponent and a 23-bit mantissa, but it gives you still the benefits of floating point without that complete range. And that's part of the newer design flows um, that machine learning models want to take advantage of. So again, we're talking about the overall motivation, and they created this specifically because there's a nonlinear increase for demand in both these areas. So this technology, this particular architecture is designed to address that. Obviously, to make this work, we need, deterministic latency. We need to have basically a low neural network latency. So when you do a machine learning model, you have inputs, you have tons and tons of hidden layers in between, and then you ultimately produce an output. Well, we need to be able to manage that effectively and reduce the amount of latency, the amount of time from the input to the output, and have a higher performance per watt. So whatever you're spending in terms of your power budget, make sure that you can get the most work and the most performance based on that. So some of the basic terminology when we're working with the AI engine, you have this two-dimensional structure. And as I just described, each AI engine is capable of doing its own SIMD data path. If you look at these different colors, they represent different types of connectivity from one AI engine to other AI engines or to other resources. The red is the most basic. So what the red is, these are memory mapped interfaces, because if you look at the picture, you can see that each tile has memory that is physically adjacent. Now, that memory is not owned by that particular tile, it's just physically adjacent. But the red shows that each AI engine tile can actually use the memory from the north, south, east, or west. So these are 32 kbyte in the original family. So the 4 makes 128 kbyte. So each AI engine tile can access that memory, north, south, east, or west. Now, how is that managed? Is that part of your code? Is that something that you have to write into the function for the kernel that's executing on this particular tile? And the answer to that is no, emphatically no. Your code only specifies what to do with the data. So when you write code, you write it as a function. The function has arguments, and you're going to pass in data as input arguments. You're going to do some processing, and you're going to pass out data to your output arguments, and that's going to be the result of whatever operation you did. So again, if you think of a basic filter, you're passing in sample data and coefficient data. You are multiplying and accumulating, and what you see on the output is the result of that accumulation based on the number of taps. So the actual movement of the data throughout this array, the synchronization of the memory access from one tile to the next, that is handled by the firmware. So you don't have to think about it. You don't have to try to manage it. In the last release, they did actually give you the option to do that. If you don't want to just let the firmware manage this, you want to get involved, sure, have a nice day. You can actually control how this starts up and how it accesses memory. But if you're doing that, you're really kind of inserting yourself in the middle of the process. And these high-speed math engines were really intended to give you extremely high throughput. So anytime you get involved, and by the way, you can, there's such a thing as runtime parameters that you can write into the code that allow you to modify certain aspects of the operation. And by doing that, you have even more flexibility. You have more things that you can do here. And again, these are RTPs, runtime parameters, but it comes at the expense of you basically putting yourself right in the middle of the processing pipeline. So yeah, you get more flexibility, but now you are adding more latency to the process. So the red, once again, represents memory mapped access to the local tiles. The dark blue is access to the streaming interfaces. So this is an AXI streaming interface. And if you look very carefully, you see that it's running east-west as well as north-south. The north-south is particularly important because even though this slide shows the AI engine here, the AI engine is always going to be to the north of the programmable logic. So when you design your system, and if that system includes the AI engines, then part of your design, and a very important part, quite frankly, is moving data into and out of the AI engine. So these are processing blocks. You push data into here, typically through what we call a shim. And a shim is basically a connection from the AI engine to the programmable logic. It's basically a streaming interface. You push data in, you process that, and then those results are immediately pushed back out. And you can either write them to memory or you can take them into the programmable logic. But we don't really store anything in the AI engine other than coefficients. When it comes to actual data, we push data into the AI engine, we process it, we push those results out immediately. So the streaming interfaces allow any tile to connect to any other tile, and more importantly, to connect to the programmable logic, because that's in probably 9 times out of 10, this is where you're actually getting the data to be processed. And this is where you're going to return those results. Then the third connection, which is shown here in the little light blue teal, that's the cascade interface. And this is what I referred to earlier when I talked about being able to use two tiles to split the computational requirements of a high-speed filter. So this is a way of connecting. The cascade connects the accumulator in one tile to the accumulator in another tile. So that's what these various interfaces are doing here. If we look a little bit more closely, we see the AI engine and the associated memory tile. The memory tile has two separate DMA engines. As you can see, it's possible for the data to come into this memory module from the streaming interface, in which case there's going to be a DMA that handles that. So there's a stream to memory map. So it's possible to write streaming data into this local memory. Correspondingly, we go the other way. There is a DMA for doing a memory map to stream. So I can write data from this local memory to the streaming channel and then probably go into the programmable logic or elsewhere. So all of this, you put it together, and these are the different ways that we're moving data throughout the AI engine array. So that portion that I just described, that's common to all three variants of this. But as we go forward, we're going to start to look at what's the difference. How does one favor one type of data processing versus another type of data processing? When you get into the actual AI engine itself, this is divided up between a scalar unit and a vector unit. So this means a given AI engine tile can operate as a scalar processor or a vector processor. The performance is with the vector processor. This is where we use the SIMD data paths and we can do the concurrent operations. This is sequential. So why do we even have this? Basically for the sake of convenience. Because if you are processing data within this structure and if you need to do 32-bit scalar operations, then you don't want to have to pass the data out of the AI engine array and then go into the programmable logic or go to a scalar processor here. You want to be able to do everything here. So this is one of your functional modes. But for performance and for throughput and for maximum bandwidth, we do the vector unit. And by vector unit, that means inherently that we are organizing the data to be processed into a vector. And that vector looks very much like work items and work groups. So let's say, for instance, I would declare a vector to use 4 lanes of data. And within each lane, I specify what type of data am I working with. So if I were to declare a vector data type that had 4 lanes and each lane was maybe 32-bit real data, then that would mean that that vector is 128 bits overall, 4 times 32. If I said that each lane had complex 32-bit data, then I would have 32 bits real, 32-bit imaginary per lane. So it would be 4 times 64, 256 bits for that. Remember that the SIMD path itself is 512 bits wide. So as you declare and use these different vector data types, you are essentially using different portions of that 512-bit wide SIMD path. I've also got address generation units. So notice I have 2 loads and 1 store. So this means that a given AI engine could do 2 separate loads in a single clock cycle. And those loads can be up to 256 bits wide. So think of maybe a kernel that's running on this particular tile that does maybe vector addition. So I pass in 2 operands, and then I perform the vector addition on those, and then I write out those results. Because this is a pipeline execution, all of these can actually happen on the same clock cycle. So I can be reading in new data. I can be performing some vector manipulation or multiplication on the previous data. I can be writing out the previous results. So when you think of it that way, you start to kind of see this is where the performance is coming from. The fact that I can actually do multiple overlapping things every clock cycle. This is why this is referred to as a VLIW, very long instruction word, because within that 128-bit instruction word, I am doing multiple operations each and every clock cycle. And this is where the performance comes from for the AI engines. So you take everything that we've just discussed, everything that we've just described, and now let's jump up to the AI engine ML. The internal communication between the tiles is basically the same with a couple of um, notes of difference here. Notice that the memory tiles are now all on one side. They're not alternating between different sides. So the cascade features can actually go along a row or it can go horizontally. I mean, I could go vertically, excuse me. So that gives the tool more flexibility when you want to do like a semi-parallel filter. But here's the main difference. First of all, each memory tile is now 64 bits. I mean, 64K. So instead of being 32K, it's 64K. So that means that each tile can now access 256K bytes in the adjacent four memory tiles. Then you have this memory tile at the very bottom. This is key. This is a 512 byte memory tile. Now, why is that there? Again, this is the machine learning optimized version. And the problem with the previous version is that even though you could do machine learning and there was a DPU that specifically targeted the Versal platform, here's the problem. I'm going to go back to the previous slide. If you looked at the way the DPU was organized, it would use a combination of the AI engines and then also the programmable logic. So it was using the AI engines for the high-speed math, where we had convolution, but then the output of that would push through the streaming channel into the programmable logic. And in the programmable logic, you would then do operations that are part of a standard um, machine learning model. This is where you're going to do your pooling, your activation, um, everything that's other than basically the convolution. So everything that you do along your hidden layers that's not convolution would take place in the programmable logic. So imagine this situation. I am pushing data into the AI engines. I am taking those results into the programmable logic. I am performing some operations here. Then those results go to the next stage of processing, the next hidden layer in my machine learning model. I'm going to do more convolution and I'm going to keep doing this, keep going back and forth. You can imagine the latency that that incurs. So that makes it really not as efficient as it needs to be. So what they do with the ML, not only did they give you more memory in each tile, but they also gave you separate memory at the bottom. And that separate memory at the bottom allows you to do operations like matrix multiplication, which is key to being able to create like a feature map, which is a big part of doing a convolutional neural network, and you're doing image recognition and classification and things of that nature. So this 512-bit, 1212-bit, 512 byte memory allows you to now do operations and stay within the AI engine array. So you're not having to push across this north-south boundary and go into the programmable logic. You can actually construct a DPU model where all of the processing is done purely in the AI engine array. That was a huge advantage. That was a huge development. Only, only, only downside to this right now is that although we have this tremendous architectural enhancement, we don't actually have the tools yet to directly take advantage of this. AMD is in a relationship with a company called DeFi, and they're going to use that company's resources and that company's expertise to update their complete machine learning inference process. So that means that the previous models, the previous DPUs, although you could use them, if you're talking about Versal, they're not going to be as effective. If you're looking at like the MPSoC family, yeah, sure, because nothing is really changing there. But for the uh, DPUs that target the Versal architecture, you want to be able to take advantage of this. And the new DPUs have not really been finalized yet. And the previous ones were based on this original technology, where they're using a combination of the AI engine and the programmable logic. So this is a huge um, enhancement, but there's not the direct support for that. When it's there, this is going to be really an unparalleled technology and a huge advantage and a great way to do machine learning in the Versal platform. So that again is the ML. So what changes in with ML2? If you look at the picture, like, I'm trying to see, like, did anything really change between that local picture and the previous picture? No. But what is here is support for those advanced data types. So your ability to use the MX6, MX9 to be able to take advantage of floating point operations in the FPGA. Because for those of you that have been working with FPGAs for a while, you know that we typically avoid floating point operations like the plague. We don't do that in an FPGA. We convert everything to fixed point data types, but using these advanced data types allows you to use these newer versions of floating point data types, be able to take advantage of that in your machine learning models and have that um, uh, benefit for your overall computation. So they ask us to match each of the AI engine variants to their respective optimizations. So signal processing, general machine learning workloads, and then advanced. So that would be really just how the boxes are organized. The original AI engines, the AI engine ML, and then the AI engine ML V2. So let's get into a little bit more detail about this, how it actually works. So this again is the M2 architecture. You have the tiles that represent individual AI engines. You have the memory tiles along the very bottom, and then you have interface tiles. And interface tiles is what allows data to move backwards and forwards between the rest of the system and the AI engines. So keep in mind, the AI engines are high-speed math processing engines. This is not a place where you're going to move data and store it indefinitely. You're not going to um, do operations here and then have the results just kind of sitting around. Basically, we push data into the AI engines for processing, and then we immediately push those results out. In fact, every operation that you do, every time you move data within the structure, it is a memory read or write. So let me go back to this slide for just a moment, because I want to emphasize the fact that when you write code for a particular kernel, you're using um, inputs and outputs and basically declaring input arguments and output arguments for your C++ function. But those are pointers. You declare your arguments as pointers. And the reason they're pointers is because every time you pass data into the module to be processed, you're doing a memory access. When you write the data out, when you write the results out, you're writing it to memory. So you have pointers. Every argument is a pointer. And that is important because you organize your data flow such that you can push data into this array as quickly as possible because you've got this really high speed resource, but you don't want it to be starved. So part of your engineering and your data flow and your architectural management and system level architectural considerations is how do I move data as quickly and as efficiently as possible. So it's going to go through these interface tiles. The native bit width on that is 32 bits. It can go up to 64 bits by combining two interface tiles together, or you could actually do 128 bits, but 128 bits is going to take two clock cycles. So we're talking about how much data can I move each clock cycle. And remember that since your data is moving from the programmable logic, this is a different clock than this. This clock was generated internally. This clock is coming from your MMCM, your PLL, whatever you configured it to be. So to the extent that you're using these resources together, you would typically set your PL clock rate to be some integer ratio of what this is. So as an example, maybe this is running at 1.2 gigahertz, which by the way, you don't control that. It's based on the speed grade part that you buy. So let's say this is running at 1.2 gigahertz. Then you might set your PL clock to be 600 megahertz because when you move data from here to there, the data path will inherently, just based on the architecture, the data path is going to be twice as wide on this side, and it's going to be half as wide on this side. But the clock is going to be twice as fast. So that means you're able to move data without any hiccups, without any excess buffering or FIFOs or anything else. Typically, the data moves from the programmable logic into the AI engine. What about accessing the NOC? Can I bring data from the NOC into the AI engines? Can I take data out from the NOC? Like maybe I want to go straight to DDR, or I want to read from DDR. Yes, these interface tiles have two different functional versions. One allows you to connect directly from the AI engine to the programmable logic, and the other set of capabilities allows you to connect to the NOC. And the NOC is, of course, your highway for any AXI master talking to any AXI slave, and that AXI slave might be a DDR memory controller. So that means that I can read data into and write data from the AI engine array directly to memory using the NOC. So part of the enhancement when we get to the AI engine ML and the MLv2 is that there's more flexibility in terms of how these connect. Each tile can still access the memory that's east, west, north, south. So a total of 256 kbyte of memory that's available. The streaming works the same. I can stream going east-west as well as north-south. And the north-south still runs into the programmable logic. The cascade is a little bit more flexible because originally the cascade was along a specific row. It would go here, it would get to the edge of the device, to a serpentine, come back this way, get to the edge of the device, serpentine, come back this way. Now, there's more flexibility. So that means that the accumulator from this tile can talk to the accumulator in this tile, and it doesn't have to be aligned on a particular row. The fact that these are streaming interfaces means they can also handle back pressure. So if I am feeding data through a streaming interface and the whoever's consuming that data cannot keep up with it, then ultimately it's like an AXI interface where it can drop ready that will propagate back to the producer, and the producer knows that, okay, great, I either have to stop or I have to throttle the data. So this is a different picture, just starts talking in a little bit more detail about what happens on a given tile. So it's a combination of the processing engine and this localized memory, and then the DMA engines that are moving data into and out of this. Again, you have a vector processor, you also have a scalar processor. This is a VLIW, very long instruction word processor, so you can do up to 128 bit instruction each time. Most of your instructions won't be that, but they could be. This streaming channel is actually moving data at a rate of 200 plus gigabytes per second per tile. Let me go back to this picture for just a moment. So when you are moving data through the array, if it goes through this, there is a 2 clock cycle latency associated with this. So as the data, let's say we're moving data from here to there. So that means the data is moving basically east to west in this case. So each time we go through one of these tiles, there is a 2 clock cycle delay. So that's the latency associated with moving data through that streaming channel. So all this capability exists in each and every tile. And this is why I said earlier that this is actually more powerful than a conventional GPU. A GPU derives its performance and benefit from having multiple individual processing elements. But those processing elements are set to handle a chunk of data. And the benefit comes from having multiple processing elements handling multiple chunks of data. But what you have here is the ability for every tile. Every tile can individually handle chunks of data, or it can do things sequentially. So there's flexibility. There's also significant performance advantage here. So we've got the two load units, two individual 256-bit loads, a store unit, the RISC processor, able to do 32-bit operations, the vector unit, which can actually support both fixed point and floating point. Excuse me. When we are passing in data for this vector unit, it needs to be organized into the vector register files. And this is the part that is not overly intuitive. If you're taking training on the Versal device overall and the AI engines in general, this is the part where it gets a little bit sticky. This is what the learning curve gets a little bit steep because these vector data types that you need to declare and the specific APIs that you're going to use to work on those are all proprietary. It's not something that you would have seen before. It's not something that you would have experienced working with any of the other families. Like there's nothing like this in the MPSoC. There's nothing like this in any of the other FPGA devices. It's a tremendous capability, but yeah, it takes a little bit of learning to be able to use these, which is why they actually developed libraries about maybe 2 years ago that allow you to kind of skip all the low-level coding. Those libraries are for filters, FFTs, DDS, just vector operations, matrix multiplies, vector additions, you name it. There's a library function, and when you use the library function, you just specify what your parameters are, where your data is coming from, and all the low-level detail is handled for you. So only to the extent that you really need to customize something or create a really, really unique application, do you even really need to code at the lower level. So there is both the architectural support, and then there's also the tool support by having those libraries. We have the instruction fetch decode unit. Each tile has 16 kbyte of memory space for the actual instruction for the ELF file that's going to be running that particular tile, which is not a whole lot, but you don't need a whole lot because your code is just the vector file. You're not managing memory access. You certainly aren't doing any other system level operations. Your code only reflects the one function that says, hey, once I get this data, this is what I'm doing with it, and here's my output. So once again, the SIMD data path is 512 bits wide. This is hardened in 7 nanometer technology operating typically at about a gigahertz, actually faster than that in most devices, all the way up to like 1.3, depending on the speed grade part. These are all software programmable. You're going to be creating C, C++ functions, but that's about the point where the recognition and familiarity goes downhill because you're going to need to use the specific APIs and the specific data types that AMD has created for this. And that's the part that you are going to be looking at something that you just never seen before. But once you get that down, you can 100% take advantage of this. There is debug trace functionality. So we can inspect the register values. We can look at the configuration registers. We can type that information out either over a standard JTAG or high-speed debug port. Standard JTAG, 100 megahertz, slightly less. High-speed debug, like a gigahertz, if we want to take advantage of that capability. So if we looked at the scalar unit, this is what we're talking about. First of all, you have registers, and the registers do a couple of things here. So I'm going to be able to do add, subtract, compare, multiply, move operations, but I have these dedicated registers, some of which is basically configuration, but notice a couple of the special registers here, like the loop variable. So if I'm doing a looping operation, let's say passing 256 samples, I want to process that, and I have a looping statement in my code that the loop bounds are set to 250, 256. Normally, when code executes, if you have a for loop, you expend one clock cycle to check the bounds of the loop because that's part of the condition for the next iteration of the loop. Well, in this technology, you don't incur that additional clock cycle because the loop variable, the loop start, the loop end, and the loop count are all maintaining registers. That saves processing time. It saves us a clock cycle each iteration of the loop. Likewise, we also have the pointer registers because every operation we do, again, every data movement, every read or write is a memory read or write. So you declare your arguments as pointers, and now the pointer math, the pointer dereferencing takes place in these registers. So it's all about optimizing the data throughput, taking some of the conventional overhead with code execution and simplifying this so that you can move data into and out of these tiles as quickly as possible. The vector unit, this is where we're doing the multiply accumulate operations. This is where we are doing the machine learning convolution. This is where we're doing the filter operations. The first thing is that the data that's coming in needs to be put into a vector unit, which is just a fancy way of saying that I need to organize my data into chunks because I'm going to feed it through this SIMD pipeline and I want things to happen in parallel. So I need to organize the data into these parallel chunks. So I'm going to have different levels of registers that support that. Let me move this graphic out of the way. So I have lower level registers that are 256 bits. These get combined in just a contiguous fashion to form 512 bits wide registers, and those can be combined um, to create a larger register. So if you think about it, this largest register is really just contiguous addressing from these four lower registers. So when would you use one or the other? Depends on how much data you're trying to process. So for instance, if I again have 4 lanes and each lane is 32-bit real data, that's 128 bits. If I have 4 lanes and it's 32-bit complex data, that's 256 bits. So I need one of these. What if I have 8 lanes and it's 32-bit complex data? So that's 8 lanes times 64. Now I jump up to 512. So I need this size. But all this is just contiguous addressing from the smaller registers. If I looked at the contents of the 512, it would just simply show me the value of these two registers put together. If I look at the contents of a 1024, I'm really just going to see the contents of these two registers, which is, of course, the content of these low-level registers. So I can process multiple um, chunks of data using this overall 512-bit wide data path. So this is doing 8-bit, 16-bit, 32-bit operations. Because most operations here are going to be using fixed point, the accumulation register is very wide because we want to be able to do multiple operations and not have to worry about saturation on the output or in the summed accumulator value. So the accumulator tends to be really wide, 512 up to 1024, all the way up to 2K bits in width. And that this allows for multiple lanes with complex data in each lane. So that's what the accumulation registers are doing for us. They're allowing us to take the parallel operations and store each one of those results individually, and then they could be summed up and passed to the output. There are also mask registers, and this is something that's new. This exact organization, this exact set of bit widths, this is unique to the V2 architecture and this set of mask registers. This is used for sparsity. And what sparsity is, when you have a machine learning model, if you go through and you look at all your weights and biases, those weights and biases that, for whatever reason, have been zeroed out for the sake of optimization, you don't want to perform calculations on those. That would just be a waste of time. That's just increasing your latency, but not really contributing to the final result. So sparsity is the ability of the compilation tool or the um, computational tool to say, okay, great, I can ignore that. I can basically not perform that particular calculation so that I'm able to compute and find an output that much faster because I'm reducing the number of computations that need to be done. So that's what sparsity is, and it allows a machine learning model to be even more efficient and have higher throughput from the beginning to the end. So the accumulation registers basically store the result of that vector data path. So if I have 4 lanes, then the accumulator is storing all 4 independent sets of data. If I have 8 lanes, then it's storing all 8 lanes. This is what the execution pipeline looks like. So each one of these represents a individual clock cycle. So your data is moving through this set of resources. Now we're right at the top of the hour, and this takes a little bit of explanation. So what we're going to do, we're actually going to take a break right now. I'm going to see what questions we have already up to now. Then we're going to take a break. Then I'm going to come back and get into a little bit more discussion about this. So I am going to bring up the list of attendees, and I am just going to open the floor right now for any and all questions.
So the DMA units that are part of the memory tiles there, the tool flow manages that level of detail, right? You define buffers somewhere in PL or DDR and destinations into particular tiles. I remember those, multi-channel DMA programming is a real bear, and the tool takes care of that level of detail, right?
Yes, it does. So all that is basically the firmware, and in this case, it's really not uh, it's not that challenging because the number of locations that it can actually be written to is pretty pretty simple. Like um, there's something called the graph code where you specify the connectivity between individual kernels and you specify the
Right,
connectivity from the graph into the
right.
programmable logic. So when you get down to the individual DMAs that are associated with a particular memory tile, their only job is to just basically write the data um, from that particular memory tile into the streaming interface. They're not really responsible for the addressing or where it goes after that.
I see. Nice.
Okay. And the kind of great thing about that is if you are wanting to use the AI engines, then you just concentrate on writing the kernel code. Like what happens when we get data?
Yeah.
I read this set of input arguments, I perform some operation, I produce some output result. I don't have to worry about the data movement. Uh, and there's a kind of a basic rule of thumb.
Gabriel Rodriguez call. Sorry about that.
Okay. All right. There's kind of a basic rule of thumb which says that the kernel code that's running on a particular tile will execute as soon as possible. So what does that mean? Well, two things have to be true. When you write the graph code, you specify the number of input samples that that particular kernel is supposed to process because the kernel is continually starting up, stopping, starting up, stopping. So as part of your graph code, you indicate how much data it's supposed to process each time, like in terms of number of samples. And that then gets translated to how much memory do we need? And so part of the firmware says, let's look at that input buffer and we need to wait until that amount of input data is in the input buffer and there's space to be able to write the output because a particular tile doesn't store data. It reads input data, it performs the particular computation, it writes to output. So it's reading from memory, it's writing to memory. So both things have to be true. The input data has to have the input buffer has to have the appropriate amount of inputs, and there has to be space to write to the outputs. And that's what as soon as possible means. When both those conditions are true, then the kernel executes. And all this is controlled by the firmware.
Got it.
Okay. All right. Anybody else have any other questions about this before we take a break and then we'll come back and look at this um, execution pipeline in a little bit more detail? All right. If not, then we will take a 10-minute break. We'll be back here at exactly 10 minutes from now, which will be 17 past, whoops, so now 18 past the hour. So again, we're getting started in exactly 10 minutes from this time point. Please enjoy your break.
You may be muted, Eric.
Oh my goodness. Thank you. Thank you. I came back and started talking and did not take myself off mute. Thank you. Thank you so much for um, interjecting that. So let me back up. All right. Again, my apologies. The just a um, so this is where we started, and I was discussing this and the importance of it being that this is how data actually feeds through the execution pipeline. And we see it's a pipeline because when you look, you can see the E1, E2, these represent different clock cycles. This is why it's possible for us to actually be loading data on the same clock cycle that we are doing a multiply operation for the previous data on the same clock cycle that we are writing out the results of the previous operation because of this pipeline structure. This is 512 bits wide, and the first thing is the vector registers up front. So this means that your data is organized into vector registers. And we keep using the same example. If I have 4 lanes, maybe each lane has 32-bit real data. Well, that's 128 bits of the total 512-bit wide. So that would be like maybe a single operand. Notice that you have these permute units. And the permute units are really important because this is what allows the different chunks of data to be individually processed at the same time. The permute units are hardwired selectors that take the data from the vector register file that you've organized and then feeds it forward in parallel chunks. So this is what allows the multipliers and the post add and accumulate to actually work in parallel is these individual permute units. And this is how we are getting multiple operations done on the same clock cycle across individual chunks of data in a given vector. The ultimate output from this goes to the accumulation register, which is then passed as an output to either the next stage of processing or to memory, whatever you happen doing with this particular output. So this is the fixed point. And because it's fixed point, the accumulator is going to be really, really wide because we want to make sure that we can accommodate multiple accumulations without having to worry about saturation or bit growth or anything else. So let's say, for example, if I have a um, maybe 16-bit operands. So I have a 16-bit data, I have a 16-bit coefficient that yields a 32-bit um, result from my multiplier. If I pass that into the accumulator is going to obviously need to be more than 32 bits because this won't accommodate any bit growth. So typically the accumulator in that case would be 48 bits. So I have 32-bit result going into a 48-bit accumulator. That gives me a ton of additional margin so that I can do repeated multiply accumulates and not have to worry about saturation. So again, that's what happens when we do fixed point math. The same unit is also supporting floating point. And if you look very carefully, you see it's the same execution pipeline and pretty much the same resources. They're just being used in a slightly different way. So the floating point unit is going to have the support for like a 32-bit floating point data type, which you could just think of that like doing 32-bit fixed, but it's actually now a floating point operation. And we see that there's going to be similar operations. We have the permute unit up front. We're doing the multipliers. We're doing the post add. Then we need to do the shift, and then that data gets written to the accumulator, and then finally the normalization for the floating point normalization, and that can then be written out to a storage register. So we've got six pipeline stages. This processes the mantissa values and then supports standard 32-bit floating point operations. Also has special support to be able to do things like a negative mantissa or any out of range values. So then that gets us to this slide, and this is really important for your planning process because this shows you, based on the data types that you're working with, how many operations, how many multiply accumulates can be done in a single clock cycle. And as you see here, if you're using just pure innate data types, you can do up to 512 operations in a single clock cycle. And this is the biggest change between the ML version versus the original family. The original family, you could do 128 8-bit operations. And for machine learning, everything's going to be 8-bit, possibly 4-bit, because we replace the 32-bit floating point data types for your weights and biases with 8-bit fixed types. So that was the engineering that was done here, was to take that execution pipeline and re-architect it to handle this data type, to make it optimized for this data type. And when I say optimized for this data type, understand that when you're using the AI engines, everything is pretty much fixed. Now you're choosing different data types, but the setup and the accumulation and the permutation, all that is fixed. This is where the performance is coming from. It's not going through a bunch of possible decision trees or decoding logic here. Everything is optimized around specific data types. And just like the previous family was really optimized for 32-bit types, this family is optimized for 8-bit types. And that means the ability to do more operations in um, each clock cycle. So what happens as we move down this list? Well, what if I'm working with 16-bit data types? Okay, but then it's going to be 128-bit, 128, excuse me, not 128 operations that could be done in a single clock cycle. Um, what if I'm working with a combination of 32-bit and 16-bit? So this might be a 32-bit sample data, 16-bit coefficient. Then I can do 64 operations. Then I get into the floating types. And if I'm using the binary float 16, which is sometimes called brain float because this came from the good folks at Google, then this is using a single precision 32-bit floating point data type. This can support 256 operations per clock cycle. The um, IEEE float 16, same thing, 256. The IEEE float 8 can do up to 512. And this is where it gets interesting when you start using those advanced floating point data types like MX6 and MX9, which are the block floating point types. The the accumulator is still at 32 bits, but notice you can do like up to 1,000, up to 1K operations in a single clock cycle, and using MX9 is 512. So this is a huge capability. This actually adds to your throughput and performance of your machine learning model using this particular architecture in a way that completely outstrips what could be done in the original AI family and even what could be done in a standard GPU solution. So that's why they're moving in this direction. Now, another caveat, and this is really, really interesting. So what about doing 32-bit data types? We can still do that. So let's say if I want to do a 32-bit by 32-bit multiplication, it basically gets immolated by decomposing into multiplications of 32-bit by 16-bit. So there is still support for you being able to do full-on 32-bit operations here, but that is not the native mode anymore. It can be emulated. And this is where things are heading. And this is kind of an important point that I want to make to you when you consider the AI engine technology. AMD is kind of tilting the scales in favor of machine learning and AI inference and things of that nature. Being able to do DSP type operations, high speed filters, FFTs, DDS, functional blocks, things like that. Not only is that still supported, but you still have the original families. So if that's the nature of your application, then you probably really don't want to necessarily get into the machine learning parts, although the machine learning parts can still support that. But like with any technology, something that's a little bit older ultimately becomes cheaper and more cost effective because the fabrication process gets more mature. They have higher yields. Those parts tend to get lower cost over time. So if you look at the complete range of Versal devices and families and capabilities, you can now say like, okay, great. I've got some devices that are super, super optimized for machine learning. I have other devices that are more optimized for DSP and communication. And the newer devices can still do DSP and communication, but they're optimized for machine learning. That's where things are right now. And you can kind of see this as the trend going forward. So this is a slightly different slide, but it makes the point that the individual tiles have all this capability built in for each and every tile. The SIMD unit, the ability to do fixed point or floating point operations, the scalar unit, the adjacent memory, and we've got the streaming channels moving data north-south as well as east-west throughout. So a given tile can connect to any other tile, either ones that are adjacent or ones that are further away. It can also connect to the programmable logic. It can connect to the NOC. It can connect to DDR. Each one of these local memories in the newer family is now 64 kbytes. So that started with the AI Engine ML and continued into the ML version 2. So that is organized as 8 memory banks. And each one of those 8 memory banks has its own built-in arbitration. And the reason for the arbitration is that, remember, each one of these tiles is individually requesting access to that memory. And the way that that works is that a given tile will issue a lock request. When we talked earlier about the firmware managing the memory access, this is part of that management, that a given tile initiates a lock request. That arbitration is built into the memory itself. And every clock cycle, it can entertain a different request. So you have 8 individual banks. You have the DMAs for managing the inputs and outputs from that. Those banks are going to be used basically as a pair. And so that allows for kind of an interleave access. And the data movers, which are your stream to memory map to stream DMAs, help move data from this tile either to the stream or from the stream into this local tile. So let's talk a little bit more about the interfaces. Like, what does a particular tile actually talk to? And let's kind of take a big picture view of this. So this gray area represents just a given tile. What can the tile talk to? On all 4 sides of this, you see the blue. The blue indicates the local access. So these are 512-bit wide accesses to the adjacent memory tiles. And this can either be north, south, east, or west. For that to happen, this tile is going to issue a lock request to that memory. That memory is going to respond when it's available. And as long as this particular tile has a lock on that memory, then another tile that's requesting that same memory would have to wait. That, by the way, If that sounds like a conflict, yeah, it is a conflict. And if you run your simulation and you do your profile, and if you discover this is happening and it's affecting your performance in a significant way, then you might want to do some constraints that force those memories to be on separate tiles. That way you don't have that conflict happening. Okay? So that's part of the constraints that you can issue. This is the cascade, the green. This is tying the accumulator in one tile to the accumulator in the next tile. So we see that this can run horizontally as well as vertically. It can connect from one tile to the next, either east-west or north-south. Okay. This is the program memory. So this is up to 128 bits wide, and this allows uh, the local storage of the kernel code that's running on this particular tile. And again, that's 16K bytes, which is not a whole lot, but you don't need a whole lot um, because the kernel code is usually very, very, very concise. And then notice this stall logic. This is of particular interest because what you have across this array of ML tiles is this systolic data flow, where we are continually pushing data throughout this array structure and we are receiving some output from that. Well, as that data moves across a given tile, the synchronization of that data movement is being handled by the firmware. And the tile itself, the actual execution code on that tile is basically starting up, executing the input data, producing an output, and then going back into a wait condition. So we have this stall logic, and this is a way of basically regulating when the tile executes. So what causes it to execute or not? Remember we described earlier this concept of ASAP, as soon as possible. This tile will be stalled or it will be waiting until the input buffer has a sufficient number of samples as specified in the graph code, and it has a granted lock request to the output memory because it has to have both the input data and the ability to write to the output before this code will execute. And up until that time, it's waiting. So technically, it's stalled. So this is a normal part of the data flow and execution and data movement throughout this array. But if you ran your simulation and you look at the waveform and you see that a particular tile is stalled for just an undue period, then you'd want to dig deeper into that. You'd want to see, okay, well, what's happening? What's happening upstream that's causing the data to not be as readily present at this stage of processing? So that becomes part of the optimization. When you do a design with Versal, in particular with the AI engines, your first goal is to just get everything working. You try to do, you know, something that works functionally based on your intended design specification. The second stage is then optimization. And optimization means you're looking at issues like this. You're looking at your data flow, you're looking at your throughput, you're looking at your latency and everything that impacts um, how fast you can process an input and produce an output. So the lock interface allows the synchronization. And again, this is managed through the firmware. You can get involved. They give you hooks to be able to do that, but typically you would not. You have a debug interface, which will let you read the values of the registers inside. You can pipe that out to either JTAG interface or to the high-speed debug capability. Um, this stall handling interface, again, if I have memory that's needed by two different tiles, and basically one of the tiles has to wait. And so the stall logic will say, okay, it's like an enable signal. It keeps this from executing until it has access to the memory. So a big part of the AI Engine ML and the AI Engine ML version 2 is this memory at the bottom. So this is the additional memory that was added, 512 byte memory. So this has DMAs, memory map to stream, stream to memory map with 6 channels. So it's a 64-bit wide, streaming interface, 256-bit memory interface. This is supporting like 4D tensor address. And so what we can do with this is we can do like matrix math, which is typically in a machine learning model. When you generate a feature map, you are taking a set of pixels from the image data, you're multiplying that times your weights and biases, and you are generating the uh, the, the the feature map. And so this is always a matrix math type operation. So your ability to do that here and store those results um, is a lot more efficient than you having to go from the AI engine array all the way into the programmable logic. And this is again one of the big advantages to the ML architecture. So looking at the interface tile, this is how we're moving data into and out of the array. This is where we connect to the programmable logic or we connect to memory interfaces. So lots of different scenarios here. This is what the tile actually looks like. So if you look at the picture, this is the AI Engine V2 memory tile. This is the interface, and this is the programmable logic beneath that. So remember that when we're moving data, the data always moves north-south through these axis streaming channels. So that's what's happening here. I've got basically a streaming interface that comes directly from the programmable logic through this stream switch, and they can continue head north, or it can go east and west and then go north. So these interface tiles are at the bottom of each column. Notice I also have access to the NOC. So this can basically talk to a NOC master unit. So I can have an axis slave here that wants to drive data maybe to a memory controller or to some other axis slave, or I can be receiving data from another axis slave, and then this is my endpoint. I actually have something here that acts as a axis slave and is receiving the data through this NOC slave unit. I also have a power on reset capability. One of the things that is different between this family and the previous families is that they used to have different tiles. They used to have some tiles that just did the PL interface, some tiles that would also do the PL interface as well as the NOC interface, and and a single tile that would do like the programming from the power on reset. In the newer families, it's pretty much one tile. It has all the functional capabilities to do any of those operations, but it's just one tile. And so it just gets used different ways, but it's not different tiles. Each tile has the same capability, but they get used differently depending on what you're connecting to. You also have, again, the DMA for situations where we're writing to the NOC master unit. So we perhaps are talking to uh, a slave or to a memory controller. So which features are part of the AI Engine ML V2 architecture? Modular scalable architecture with distributed memory? Yes. Integration of 2D array with tiles to increase compute density? Yep, sounds good. Memory tiles with 512K byte to support like a 4D tensor address generation? Yes. Everything except this last one. There's no dedicated hardware for real-time processing. That's part of the V2, but not the AI engine. So here's a quick overview looking at the original AI engine family, the AI engine ML, and then the AI engine ML version 2. So this is what we're finding in the Gen 2 product. And the way the memory is laid out, all lines are identical as opposed to alternating, kind of creating a checkerboard type effect. The cascade interface is now 512 bits wide. The reason this was 284 bits wide was because 284 bits was the width of the accumulator. Now that the accumulator is wider, then the cascade is wider. So it's 512 bits, and it can go horizontal and vertical as opposed to just horizontal. The streaming interfaces in the original families, we had two 32-bit ins, one and two 32-bit outs. Now it's a single 32-bit in and a single 32-bit out. The memory, what can be done in a single cycle, we can basically do 256, 512 bits overall load. This is two separate 256 bits and one store. And here, that number was the same. Actually, this is not correct. This is a typo. In the original family, you could do two separate 200 or 128 bits. So it's total 256 bit and then 128. So this would be half this number. In the newer families, because they went from 32K byte to 64K bytes, that's when the numbers doubled. So yeah, this should actually again be 256 slash 128. And the newer families, you also have a little bit more flexibility because now you can go not just from the local tile, but then to the neighboring tiles in a way that's more flexible. So you can do all the way up to 1024 local 512, 1024 load 512 store. Then if you look at this, the number of 8-bit operations you can do increases dramatically from 128 to 256 all the way up to 512 with the newest devices. The native support for data types and the original families, it was really optimized around 32-bit data types. In ML, they started supporting more 8-bit types and 16-bit types, including bfloat 16, but now you have all of that plus the MX6 and the MX9. Those local tiles are again 64K byte as opposed to the original 32K byte. The local memory DMA, 32-bit streams, um, overall 128-bit wide interface. In the newer families, it's a 64-bit stream up to a 256-bit memory interface. The memory tiles themselves only exist in the ML and the ML version 2. That was not part of the original families. The interface tiles, they used to either be PL or NOC. Here it's a single type interface tile. And the control for this is external before. Now you also have a microcontrol module that can be used to actually control certain aspects of operation. All right, so again, key differences between the overall AI engine ML and MLv2. This slide shows the families, and these are the families with different versions of this. So you pick and choose based on what your functional requirements are. And again, if you're doing machine learning, you absolutely want to be able to take advantage of this newer stuff. Um, and hopefully, I'm really, really hoping that sooner than later, you'll have the complete tool support. They'll have new versions of the DPUs that actually target this new technology and take advantage of all the resources that we've been looking at over these slides. So which of the following is the main difference between AIE and AIE ML22? Um, okay, the first one is wrong. The second one is wrong. The third one is correct. And the fourth one is wrong. So only the third one here is true. Okay. All right. Again, we're going to take the time to entertain questions. So I'm going to bring up my participant view and I will just open the floor for any and all questions at this point.
So earlier, you mentioned the Vitus AI tool, and it sounded like what that did for you was allow you to take your AI training data and prune it back, change the data types and stuff so that you can work with the ML Versal parts. Is that I'm interested in that because you need that tool to actually develop an AI application. Is that like a purchase tool, or do you have to qualify for that tool? Assuming you have the chops for that, how does one get that tool?
I don't know what the cost of the tool is. Like, interestingly enough, Vivado requires licensing. You have to pay for that, but Vitis is free. So
Right,
I don't know if Vitis AI is also free, but you're absolutely correct in that you have to have that tool. And part of what the design flow is doing here is, let's say you're a data scientist and you're interested in doing some machine learning and porting your model to an FPGA based implementation. Xilinx knew early on that you're never going to get anyone to adopt FPGA based implementation if they have to learn FPGA design, if they have to get down into the bowels of the
right,
technology and understanding COBs and registers and DSP blocks and things like that. So they intentionally created a very, very abstract data flow. And it starts with Vitis AI because the output files that you're actually generating will be different based on whether you're using TensorFlow or whether you're using PyTorch or whether you're using Onyx or whether you're using Caffe. Each one of those uh, can be used for the training purpose, but each one is a separate environment and each one outputs a different set of output files. So what Vitis AI does, you invoke the tool based on the particular framework that you're interfacing with. And now it's set up to take the outputs from that particular tool and then do the conversion that you just spoke of, which is to convert the 32-bit floating point data types for your weights and biases into 8-bit fixed types, and then allow you to target a particular DPU. And the DPUs are optimized for each separate architecture. There's one that targets the Alveo, there's one that targets the MPSoC, there's one that targets, there are two different ones that target the Versal devices, but each DPU is sort of like an overlay. And by overlay, I mean, when you think of things going into the FPGA fabric, you you think of the synthesis process, the mapping, the place and route. Well, if you have an overlay, it's really more like a hard macro. Even though it's being implemented in fabric, the individual routes, the individual block, the mapping, all of that is pre-configured, and that makes it very deterministic. But that's what's necessary for AMD to be able to market this as a viable solution, because nobody's going to get into the FPGA architecture and details if all they're really concerned with is, does this work for my particular model? And does it save me? Does it actually help me achieve an output faster, like in terms of latency? Is it more efficient in terms of area utilization and power and everything else, which makes it an edge-based uh, solution for me that works really, really well. So it's inherently and it's intentionally very, very abstract. But as you noted, it starts with that tool. So if you're interested in doing machine learning at all, then you need to understand the Vitis AI. And unfortunately, that's where the current gap is. Um, Previously,
right.
all they really were supporting were convolutional neural networks for doing image recognition and classification and things of that nature. There was one, they had one developer as an RNN, and for doing speech recognition and things like that. Um, but most of the models were CNNs. And the problem, the problem with the Versal model, as I said, was this idea of using both the AI engines and the programmable logic and continually having to go back and forth between the two. So when AMD bought The company is DeFi. I don't remember the name of the company. It's something very, very similar to that. They bought them specifically for their machine learning capability. And what should come out of that is a new class of DPUs that are updated, that target these newer technologies to take advantage of the resources that we're talking about, and maybe, just maybe, allow you to actually develop a complete model within this technology, which means you'd have to be able to do the training as well as the inference. I've seen some documentation that alludes to that, but I have yet to see any concrete actual examples, much less any training material around that. But that's where things are headed. And for customers right now, you're kind of left in a little bit of a limbo, because you can already see these new features, but how do you use it? I mean, how do you actually take advantage of this? Is the next version of Vitis AI should be able to do that, but the current version of Vitis AI is really still just supporting the older stuff.
Okay, yeah, thank you.
Okay. All right. Other questions? Okay. All right. If not, then we are going to move into our next topic then. So remember, we're going to conclude today. We're going to get to about 11 a.m. and then we're going to do a lab exercise. And that lab exercise is going to take advantage of some of these new multimedia capabilities. And more importantly, it's also going to introduce you to the start of the compilation process using Yocto, which that's going to be really interesting. And that is very much the roadmap for what you should be doing going forward. So we're going to go through an example of downloading the repo file, setting up the Yocto build environment, and that will be the groundwork for, what you need to do going forward. So let me bring up the next set of slides. So it's safe to say that if you were to just try to put into really, really simple sentence, what's the big difference between the Versal Gen 2 product and the original? You would definitely start with the ability to cluster the APUs and RPUs, going from having two APUs up to eight, going from having two RPUs up to 10, and the ability to run those in lockstep mode or independently to be able to achieve higher levels of safety and certification. Absolutely huge. That's very meaningful. The second thing has to do with these hardened video processing blocks. These multimedia hard blocks which is what we're going to discuss in this section. And if you put those two together, you can immediately see what industries they're targeting. They want the virtual product to be something that's more easily adaptable to an edge-based deployment, where you're going to have the need for extremely high throughput at very efficient power ratings, and also tremendous, tremendous safety, especially if it's going into an ADAS system or it's going into some industrial application. So the third key area of enhancements for the V2 is all the new safety features, the ability to do cryptology to do a lot more encoding, decoding of your data, not just your configuration data, but your actual um, real-time usage data. And there's a lot more features that support that. So again, three areas: the processors and the clustering, the hardened video blocks, and then the security features. Those are the three things that really distinguish the V2 product from the original family. So now let's talk in more detail about those multimedia hard blocks. We're going to describe each one of these and look at some of the features and functionality that you get from this. We saw this slide at the beginning of class. This is kind of an overview. And again, you see the ability to cluster your processes. Excuse me. It's like every time I go to bring up my cursor, I get like lost for like 5 to 10 seconds as I'm trying to find the right button. So this is a major feature. The AI engines being able to support these advanced data types like we just discussed, the improved safety and security. This is huge. You could do things with the Gen 2 product that you could never do before. And then these hardened video processing blocks. This is what really distinguishes Gen 2 from the previous families. High-speed memory controllers, yes, the fact that you're not doing DDR5, but more importantly, you also have inline encryption, decryption. And you know, this particular level of the integrated GPU and then everything else, we could argue like, okay, yeah, this is slightly enhanced, but these are the things that are really new and different. So let's talk first about the VCU. And this is what we're gonna do a lab exercise where we're gonna at least bring this up, go through some really basic configuration. The whole point of the VCU is to give you real-time compression. And because it is a hardened block, we're going to have low latency and less power consumption. Anytime you look at, say, an FPGA architecture, anything that has to be done in the fabric means that you're building it up from individual slices and COBs and lookup tables and routing. It's always going to wind up taking up more area and dissipate power. On the other hand, if we make it a hardened block, it can be faster at less power. So that's why in the FPGA technology, anytime you see them introducing something that's a hardened block, is for that very purpose, to be able to give you the utmost performance at the lowest possible power. So this is supporting the most standard video encoding, decoding um, protocols that you would likely be using, H.264, 265, and JPEG. This can support up to 4K ultra high definition at 60 frames per second, up to 8K at 15 frames per second. That is really high performance. It can do progressive encoding for the H.264, 265, and if you are interfacing to an older system or an older set of input output blocks, then it can also support interlace. Um, uh, basically, the difference between progressive encoding and interlace is how the input data is being read and organized. And interlace is the older standard, so there's still support for that. So you could do up to 32 different streams. So that means 32 completely different input streams up to that maximum bandwidth of 4K, 60 frames per second. So this is how it looks in more detail. I've got up to two VCU tiles per device. And each tile has an encoder and a decoder. And this is communicating through 6 AXI-based interfaces that allow you to move data into and out of this. This also allows for your basic controls, setup, configuration, everything that you need to operate that particular module. Each tile has two 128-bit wide interfaces for video, two 120-bit wide interfaces for control for both the encoder and decoder side of this, another slave interface for external configuration, and then a AXI Lite interface, which is just um, like register configuration and things of that nature. So you have this picture where a given tile has both the encoder and the decoder. And notice that each one of these blocks has an MCU, which means there is a microcontroller there. That microcontroller is a RISC-V controller. So that kind of shows you again that AMD is fully adopting the RISC-V architecture because in the past, anytime they needed to implement something as a microcontroller, they would have used the microblaze architecture. So in the newer devices, you see they're already leveraging the capability and the flexibility of the RISC-V um, MCU, and that's what these are. Both the encoder and the decoder, totally separate, but each one of those is a RISC-V processor. So the encoder side of this, dual core block, 4K, 30 frames per second per core. So you can combine both the cores, and now you're able to do 4K at 60 frames. And this has a hardened level 2 cache. That's also another important feature here that in the past you might be like using Ultra RAM or Block RAM. This actually has a hardened level 2 cache. So um, that's going to give you single cycle access to memory. The decoder engine is a single block core, 4K, 60 frames per second decoding. You have a bridge unit that allows you to basically manage the memory transactions from one stage from the input to the output. And then this makes sure that the output from this block is also just very, very smooth and you don't have any glitches. Those controllers, again, are RISC-V based. So they are a set of dual, one for the encoder, one for the decoder. It's a 64-bit version of that architecture, and it's responsible for all the operational management and control. So you've got firmware that uh, controls the internal operation. That's all that is running on these RISC-V processors. You have individual tasks, service interrupts, coordinating the data transfers, the predefined task list. All of that executes on these processors. These connect externally to a 32-bit AXI interface and then use a AXI Lite interface for peripheral access. So these are the building blocks that make up this overall VCU tile. If you compare this to what was being done before, so here's the like maybe like the Zinc Ultra Scale, which had a video codec unit as well that could do 264, 265 encode decode, which was the predominant industry utilization. This also supports JPEG. The performance here was uh, basically up to ultra high definition 4K at 60. This can do um, 4K pixels at 60, so really should be about the same here. But you can also go up to 8K at a reduced rate. This has a lot more support for different chroma. So depending on what you need for individual quality of the picture, there's more support here. The number of bits per color is increased. Rather than just 810, it goes up to 12. The buffers, rather than having to do things in the programmable logic, you have that hardened cache. This only supported raster scan, but this can either do raster or it can do tile. And tile is going to be more efficient. It's actually going to save you a ton of memory. The frame buffer compression support, you couldn't do that here. Here you can do it. And for low latency modes for the encoder side, you have up to 4 streams, the decoder up to 2 streams. Here, it just cuts it in half so that it allows you to basically still be able to support multiple streams if necessary on the encoder side, but be able to maintain the low latency operation. All right, so before I go there, So again, this is the introduction to the VCU. We're actually going to go into a lab. We're going to talk about the VCU, do a little bit of setup in the IPI tool. The other parts are the image signal processor and then the Molly. So that Molly, this is again based on the GC78AE automotive enhance. And part of that enhancement is being able to have separate data streams, being able to create isolation and independent operation. So this is meeting the uh, higher levels of the automotive safety requirements. It integrates directly to the programmable logic as necessary. It's operating at up to a gigahertz performance, accelerating 2 and 3D graphics at 4 frames, from a 4K at 60 frames per second. So if you think about again where this is heading, you can put this into an ADAS system, and you really now have not just a single chip solution, but you have something that is optimized for processing that input data. So if you combine this with the machine learning, so once you actually have this input data, you're able to process, you're able to build an effective model for classification, recognition, things like that. And you have these hardened blocks, so you're able to do much faster processing and support higher data rates. Again, as I mentioned on yesterday, you think of doing a graphics pipeline in an FPGA, things that you concern yourself with is, first of all, throughput. How much data can I move? Because FPGAs are not necessarily known for being the most high-speed resources. But when you're looking at this platform, the reason that they're using these hardened blocks is to be able to give you exactly that: high speed, throughput, low latency, low power dissipation. So for an edge-based deployment, you want all three of those. And this is supporting all the industry standard APIs, Vulkan, OpenGL, and OpenCL. The difference between them just being what are you trying to do and at what level. If you're just concentrating on graphics, then this is probably your best choice. If you're doing graphics and also some other parallel computational things, then OpenCL. If you want to do graphics, but you want to do it at a lower level, have APIs and libraries that tend to be more granular, then Vulkan. So that GPU is organized into two separate slices, and there's a partition manager, and this can be dynamically set to where you now have the uh, separate operation and isolation. And this is the big feature behind the Valhalla architecture. And this is also what makes it automotive enhanced, is the ability to have that separation and isolation. So you have two cores, then two slices and then two cores per slice. The partition manager allows for the separation of the two, and you have this runtime shader core allocation. So you have two shader cores per slice, and the shader core is what's actually doing the majority of our computation here. You have dedicated AXI interfaces, AXI A, B, and C, depending on how the data is being read. And this is also supporting that isolation and independence of one side from the other side. The fact that you can do a tile-based rendering is great because this is going to significantly reduce your memory access, which means things run faster, you minimize power, but you still maintain a really high level of visual quality. So comparing this to the previous families, the, the previous one was Utgard, and then as I said yesterday, the company that ARM bought to absorb their technology for um, not VCUs, but for graphics processors, was a Norwegian company. So that's why you have all these references to Norwegian culture. So the number of cores before was two, now it's up to four, 12 gigaflops up to 268. Just OpenGL support here, version 3 2.0. Now more support, OpenGL, Vulkan, as well as OpenCL, which you could not do that at all before, up to 4K resolution as opposed to 1080p, and up to basically 1 tera op, when you're doing AI performance, something that you really could not measure or quantify with the previous devices. So the last block here then is the image signal processing. And this is basically your front end. Well, your front end is, of course, your camera. Your camera is likely feeding through a MIPI interface, which is packetizing the data and then passing it to this image signal processor. And the image signal processor is necessary because if we are feeding this into a machine learning model, then we need to do pre-processing. And this, if you are configuring a machine learning model, one of your choices and one of your options would be like for the pre-processing and for the post-processing, how do you want that to be done? You want that to be done in the programmable logic, or do you want that to be done on the processing subsystem? Like you could move that to like the 853. So I'm talking specifically about the MPSLC implementation. So one of your choices for your pre-processing, and your pre-processing means everything from color balancing and correction to cropping the image to the exact size that's necessary for your machine learning model. Well, that work can either be done on a processor or it can be done in the programmable logic. And one advantage to putting in the programmable logic is that now you can use the kind of typical hardware acceleration techniques like unrolling loops, doing things in parallel, exploiting the concurrency. But with this technology, they're giving you yet a completely different approach. Now, this is only on the edge-based series. So this is only on the devices that are really already geared for going to the field for being implemented in a actual field-based deployment. So you now have the option to bring in that original data and do all of your processing using this hardened processor. So you feed this out and now you go directly to a machine learning model that's maybe doing detection, classification, or just display rendering. Any type of downstream application, you can do the upfront image processing here. And so the way this is going to be built is you've got each tile, which has two instances of these building blocks, and you have a maximum of 5 streams that can be supported per tile. So you either implement this as 3 on one half and 2 on the other, or 4 on one and then 1 on the other. So a maximum of 5. So you can have a little bit of flexibility in terms of how you configure this, but you're supporting either a single or multiple stream configurations. This is up to 8 megapixels at 60 hertz or 12 at 45. Each instance also has dual output capability, and each instance also includes both image processing blocks. So again, this is allowing you to very, very easily, very efficiently do the initial processing, get the data ready for the downstream blocks. And notice that your outputs here can go directly to the NOC. So this becomes a master driving onto the NOC master unit. The slave would then be um, like um, the graphics processor unit, the GPU, or possibly the encoder. So the two different modes here is either none or the multi multi-stream mode. So if it's none, then we just have a single input stream. And if we're doing that, then these are our options. I can do basically live in, live out, which means I could actually support incoming video stream and output a video stream. So live video input, live video output. I could also do live video input and then memory on output. So I can take that live video, I can process it here, and I can write the results to memory. I could also use this in a situation where I'm reading from memory and writing back to memory. So I do some processing, I pull the data from memory, I process it, I pull it back into memory. So these are the 3 different ways I can do this. If I'm doing multiple streams, then I'm a little bit more limited because now I can do basically live input and write it to memory. So I don't have the ability to output multiple live outputs, but I can take multiple streams and write them to memory. So four input streams, up to four input streams with the outputs being written to memory. Okay. So they ask us to identify which Versal hardened IP blocks are going to do which functions for us. So on the left-hand side, the primary function provide high performance graphics rendering, compute acceleration, enable efficient encoding, decoding of video formats, and then real-time pre-processing of the data. And um, basically, obviously, the first one is going to be the Mali graphics processors. The encoding, decoding is going to be the video codec unit, and the real-time pre-processing is going to be the image signal processor. So once you start utilizing these various interfaces, then you've got a ton of ways of reading data into and out of this. So you've got USB 3.2, able to operate at the up to 10 gigabit level. There is also support for DP, which is the DisplayPort 1.4. There are earlier versions of the display. This is the latest version of the DisplayPort. So this is, kind of put you on par with the most up-to-date utilization of that. And that can do like 8K video input. You also have EDP, and then you have video audio STP inputs. So all this is part of the DP um, protocol. And basically display port, for those of you that are not familiar with it, a lot of things in the past have been done either, I mean, originally it was done, of course, over the VGA, then HDMI replaced that. But when you do these industrial applications or these automotive applications, HDMI is not necessarily the best suited for those environments. So that's why the industry created the DisplayPort protocol. So that's what's being used in this case. There is, of course, support for HDMI, but this is more likely what you would be using. So you've got an Ethernet MAC supporting up to 10 gigabit. You've got two PCIe, uh, basically Gen 5, 4 lanes. And you've also got integrated GPU. So all of this, all these building blocks and interfaces are supporting a variety of different multimedia blocks. So if we look at this in more detail, let's say, what about the USB, the display port, and then the HDCP, and the HDCP is the security interface. So for this, I've got five key building blocks. As the display controller itself, taking the data from streaming data from the PL, and then the AXI for control. Then I've got the transmit controller. I have the HDCP. So again, if I were doing some encoding, if I had a really secure environment and I needed to encode this, then this is going to um, use a true random number generator and provide a key to encode the data. Then this is going to feed into the USB 3, basically Gen 2.1 dual world conversion um, controller, and then ultimately out to a USB 3 PHY. So if I look at each one of these in a little bit more detail in terms of what are you doing, the main one, first of all, I got to fetch the video graphics data that's related to audio from either memory or most likely from the programmable logic if I'm doing real-time processing. Then I need to send this combined video stream to the display port. Other things that are going to happen here as part of the DisplayPort protocol, I'm going to do blending, I'm going to do chroma subsampling, and then color space conversion, all of which would be essential because, again, this is me outputting to a display. So these are the kind of operations and corrections and um, enhancements to the image before it displays. I also have a bypass mode. So basically I can go from one, maybe 8K 30 frame stream up to just four independent streams go directly to this DP transmit module. And then all four streams will have their own set of timing, their own set of resolution. So if you look at the DP controller itself, this is basically forwards the video from the controller over just basically a standard Type C USB connection. And this is supporting basically an alt mode for USB traffic, either one or two configuration. And the capabilities of this is to have up to four individual streams, as we just talked about. I can have a single stream up to 8K at 30 frames per second. Again, the protection from the encoding unit and by four link operation for PCIe over a Type C connection, and then the maximum raw bandwidth. And this was one of the enhancements to the DP standard. Well, this is part of the reason why they're supporting DP 1.4 is that the raw maximum bandwidth on this is up to 32.4 gigabits. Effectively less than that because of the overhead and the blanking and things like that. But this is the highest data rates that DP will support currently. So the main DP TX interfaces, I've got the pixel interface. So I've got parallel input output, and then this is going to be configured to either handle just one, what we call basically like a single pixel mode or multi-pixel mode. And it just depends on how the data is being organized and how we're going to process that. The audio interface comes in with this I squared uh, as audio input interface. Then the SDP is used like for secondary data packets, which then become part of the overall visual effect. And again, the encoding. So this is an intermediate between the HDCP controller and then the external repeater PHY. And this is where the encryption takes place. And I've got a couple of different streams, but this is pretty much already set up from a protocol standpoint as to how the encryption is going to be done. So just a little bit more detail on this. If you did need to do a secure transmission of the video data, then that's where this resource comes in. So this forwards information from the receiver or repeater and then basically returns um, specific output to the controller. So you've got the key stream port, you have different interfaces, and then you have the identity interface. The point is that we can use this should actually be kind of bidirectional here, to encode the data, to actually take the video data that's being sent to the output port, and we can do encoding or decoding on that. So if it was pre-encoded, then we can decode it. If it's necessary to encode it at this point, then we can do that. The other portions of this, you look at the USB 3.2, the DoD controller, you've got the 10 gigabit operation. This is simultaneous transport. And one of the great things about this, it gives you a lot of flexibility. This can do both the USB and also the display port. And that display port can be running 1.4, but still be using the um, the encryption. You had Type C lane selection, and again, this is again one of the reasons that they're moving to display ports, so you don't have to have HDMI connections. You can just use Type C USB connections. The display controller itself streaming to or from the PL, and then There's also a USB 2.0 functionality, and that is used through a separate PHY. So we can't have everything running at one time. So there's a little bit of overlap. There is a MUX here. So we basically configure this as a transmit receiver, single one for the USB, a transmit receiver with also the display port or four display ports. So those are the different possibilities for what comes out of this MUX. So we are configuring it based on our application, but that's great because now we have the flexibility based on our specific use case. You also have support here for the PCIe and the 10 gig Ethernet MAC. So the PCIe, you got two PCIe Gen 5 modules. And so the PCIe is, of course, going to talk directly to the gigabit transceivers, going to talk to each transceiver in that particular quad and give you support for that, along with the pipe MUX logic, which is handling the data and clocking between the individual PHY and then the IP blocks that are actually driving in the data. This supports, among other things, like a inter-core kind of look back feature. So if you want to kind of build in some testing, if you're trying to do verification, then that feature comes in handy. And this is a way to be able to implement and also do a functional test of the gigabit transceivers and control it from the programmable logic. This HSDP, that's the high speed debug port. And remember, again, this is for you being able to do testing and tracing at a gigahertz clock rate. So a couple of key features of the PCIe, as part of the protocol, it's always going to be downward compatible. So when you do the link training, it determines what the maximum rate is for the link partner, and then it can go all the way down to PCI Gen 1 if necessary. You have two independent four-lane controllers. They could be, you know, four lanes, RC or EP dual lane, two-lane RC, and then or two-lane EP. This is built as 256-bit inbound, outbound AXI memory map interfaces that come directly from the PCI controller. This uses the Aurora high-speed debug ports at around 12.8 gigabits per second. And the other possibility is to run this as a one-lane Ethernet interface with up to 10 gigabits. So this is kind of a different graphical view, and this is showing, and again, you have a MUX here, so you have different possibilities for how this is configured. So you're not going to be doing all of these. You kind of pick and choose for your particular application. So question, which of the following statements about the multimedia interfaces are true? That the HDCP 2.3 is required for secure transmission? Yes. The DisplayPort TX version 1.4 supports a single stream video up to max resolution. Actually, single stream can go higher than that. The display controller can send and receive data directly to it from the PL. That is true. And the USB 3.2 DRD controller allows simultaneous transport of USB up to 10 gigabits per second in DPU. Yes. So that one is true. So the first one, third one, fourth one are true. Okay. All right. So that is our what was going to be our final lecture topic. So we are going to take a break. We're going to entertain questions, of course, and then we're going to come back and we're going to start working through the lab exercise. So as always, I'm going to go to my participant screen and I'm just going to open the floor for questions. Okay. All right, then let's be back here in 12 minutes from now. So that'll be 50 past the hour. And we're going to get started with this lab exercise. All right, please enjoy your break. I will see you then. Okay, we are back. And I'm actually switching to a different machine so I can run the lab exercise from here. You guys want to do me a favor? Just give me a quick audio check since I've changed machines. Just let me know that you're able to hear me and that I'm coming through loud and clear.
Yeah, we can hear you.
Okay, thank you. Thank you very much. All right, so we're going to walk through an exercise where we are generating the hardware and then the system files for a multimedia system. And then, as you can see, based on the objectives of this lab, we're also going to get into preparing the Yocto environment using the repo tools and the EDF manifest. I have to make a little bit of a confession here. The way this exercise is written, they are really doing kind of two different things. And both things would be necessary in an actual design, but the way that they're doing it in this particular exercise, they're not really related. So yeah, you have to do both things, but they're not really tying together the first half with the second half. And I'm kind of pointing it out to you because after reading through the lab like multiple times and using it, I'm like, okay, yeah, there's a bit of a disconnect here. So part of the problem with doing labs around the Versal Gen-2 product is that the actual support in the software has been slow. I mean, they've been announcing this product for quite some time now. You can see all of the presentations like the one that we just did that shows all the fabulous new features, but where's the support? Where is the software support? And that also creates challenges for the training organization because all the dedicated trainers like myself, we've been asking the customer education group, hey, when are we going to be able to, train customers on all these new features and all these, exciting new innovations in the Gen 2 product? And that's when we found out that, well, we can't give you training on that because it's just not really being directly supported just yet. So this particular lab was first in a class that they just created, which goes into a deep dive on all the multimedia processing stuff. So you just saw like one section that kind of highlighted each one of those and gave you a little bit of detail. Well, now there is a full day-long training that goes into each one of those topics in a lot more detail. And when that class first came out, there was a single lab exercise in it, and it's the same lab that we're going to go through here. Well, they've now moved this lab exercise to the Versal Gen 2 training. So it could be, same exercise can be done in either class. And what I have concluded from all of this is that, okay, they wanted to create this class to highlight the features, and they obviously needed to create some kind of a lab exercise. So they decided to kind of put two things together. Let's show how you would go through and maybe configure the video codec unit. And let's also show some of the features of this embedded design framework. And you may recall yesterday afternoon, that was one of the last things that we were talking about was this introduction to the embedded design framework, which is the new software design flow that AMD is now offering and supporting for customers. So they kind of put these things together and it seems like they're related, but they're not. They didn't really tie the loop just yet. So I'll explain it to you as we go a little bit further. But if you look at the objectives of this lab, it says one, we're going to create a new Vivado Design Suite project. We're going to configure the VC2 IP. Then we're going to generate an example design. Great. We can go into the example design. We can look at what features got generated there. Then they say generate the device image and export the hardware. So that's absolutely what you would do. You would take what you've done in the IPI tool, you would export this as a .xpa, and then that XPA file goes into either Peta Linux or it goes into Vitis, or should go into this Yocto flow. So then we jump to, well, let's prepare the Yocto environment using the repo tool. And the way I had described this to you before was that as AMD is encouraging customers to move toward using Yocto directly, they want to make that at least feasible for you by simplifying what you need to do to get started. So Yocto is based on individual recipes and layers. And if you're trying to do a Xilinx design and you're just using native Yocto, then you'd have to go figure out all the necessary recipes and layers that are specific to the AMD technology that you're targeting. So what they've done to make that easier for customers is they now give you this, basically this manifest. So you can just use the repo tool and dial up this specific manifest. So that will download all the necessary recipes and layers so you'll have them in one place. It also then sets up the execution for the build environment. So it really makes it easier for you to get started with Yocto. And that's what we're going to do in this particular exercise. And so it seems like we are kind of working on the same application from the beginning to the end, but it's not. We're going to do the application and then we're going to go set up Yocto. But what we're doing with Yocto is not directly related to the first application. So having said that, let's get into the lab exercise itself. So they always give us an introduction, kind of describes the basic concept of the lab or whatever it is we happen to be talking about. And in this case, we're talking about the VCU, one of the hardened uh, um, multimedia process blocks that are part of this V2 architecture. So in order to build a multimedia pipeline, we need to have both the hardware, the software design files required, and this gets exported through the .xsa file after you have created this in the Vivado environment. You have this little boilerplate information that talks about understanding the lab environment, and that's just unique to this virtual machine that we're using to run it. So we can go past all that. And then that gets us down to the actual general flow of the lab. So we're going to create a Vivado project, add and configure the IP, open up the example design, generate the device image, export that as a .xsa, then set up the Yocto environment, configure the system. And we would build the images, but building the images actually takes hours. And I probably don't even have enough memory on this machine to get through that. So we'll get right up into that point and then we'll show what the commands are, but we won't go as far as building this. So the first part of this exercise is to open up Vivado. So let's do that here. So I'll click this. This starts up the Vivado tool. Once this opens up, we are going to create a new project. And that project is going to be located in a specific location. This is almost the same as like going into Vitis and creating a workspace, but this is the project space for Vivado. For those of you that are very, very familiar with Vivado, you know that Vivado can also be run in a non-project mode where you're scripting everything and you don't then have the overhead of a project, but then you also don't have the convenience of a project. And that's it's designed so that as a user, you can kind of pick and choose which is more important to you. So we open up the tool, we say we want to create a project, start through the menu, and the project that we're going to create, in this case, we're going to call it VCU design. Excuse me, VCU 2 design, actually. And this is going to be located in the training folder under this particular exercise in the lab in the hardware folder. One thing you should probably note here, and this is actually an important point. Notice that there's a hardware folder and there is a software folder. When you are using the Yocto flow, you will definitely want to organize your design into two separate folders because there's a lot of software components that you need to create, but you're going to be exporting the hardware components. So it's better, much better, and it's recommended that you actually have a distinct hardware and a distinct software folder. So we are selecting the hardware folder, excuse me, as the location where the Vivado project is going to be set up. Okay. And we say don't create a sub project subdirectory because we already have a unique space. So we click on next. All right. And this is complaining about the fact that I already did this. So what I'm going to do, because I still want to walk through these steps. So I'm going to actually I'm going to quit this for just a moment. Yeah, I walked through the same step. And so Bovado won't let me create a same project by the same name in that same location, but I can remedy that simply by just getting rid of everything that was generated before. Because initially, everything in these folders are empty. There's no example design, there's nothing. So let me just get rid of everything. So this is how the lab starts off. I have a hardware folder that is empty. I have a software folder that is empty, okay? So with that, I can go back to these steps and go back to Vivado, say that I want to create a project, call it, the name they wanted was VCU2. So back up to here where we create project and give it that name, VCU2 design in that specific location. And this is going to be an RTO project, and we're not specifying any sources at this time. By the way, when we say RTO project, that means that we're not starting with an existing net list. We're actually going to do compilation, synthesis, all of the operations in this particular project. So if you were starting like with a existing net list, then you would be choosing one of these other options. So I've given it um, the name indicated where it's going to be written to, selected that it's an RTO project. And now I get down to step 1-4 where I am selecting the target device. So I'll go to next. And since I indicate do not specify sources, it didn't take me to the menu where it's asking me for input files or constraints. It just took me directly to specifying the board. So I could either select an individual part, which is what I did yesterday, or I can select a particular board and I can type in VEK and I want the VEK 385 Rev B. So click on next. That brings me to a summary screen and I can now click finish. So this will take just a few moments and I will advance the lab instructions up to this point. So that created a completely empty Vivado project. And now I'm going to start creating IP. And of course, when you do any kind of embedded design, most of your work will be done in the IP integrator. So I'm going to create a block design. I'm going to leave this with the default name of just design one, click OK. This is going to then open up the what we call the IPI2, the IP integrator, but the file that you create is a block design file. So similar to yesterday, I want to change the screens just a bit so I have a little bit more space for visibility. And I'm going to pull from the IP catalog. So I'll click on the plus and I will click VCU2. And this is basically the Versal video codec unit for the Gen 2 part. So I've added that to the canvas, and that brings us down to step 2-3-3, where I double click this to start configuring it. And in this case, I'm going to configure it to be both an encoder and a decoder. So I make those selections here on the first pane, and I'm not changing any of the other default settings here. Then I start specifying the details for both the encoder and the decoder. So I will click on the encoder, and they didn't really change anything. In this lab exercise, they just left everything at the default. So you see the particular coding standard. You see there are different choices here, but we didn't change anything. We didn't change the resolution. We didn't change the color format or the source format or anything. Likewise, for the decoder summary, same thing. We just left everything as the default. So really what they're doing with this lab is more so showing you how to bring this particular module into the IP integrator. And if you were going to individually configure it, then this would be the menus that you would use. The fact that they don't actually have us doing anything, it makes it a little bit anticlimactic, but nonetheless, this is what we need to do. Then the next part of this is to generate an example application design. So that feature is now in the menu. And I say now in the menu because that's a change between 2025.1 and 2025.2, that the application example is now part of the menu. So you go here, and this is basically going to set up an example design so we can see exactly how the encoder block is talking to the processor and then also talking to memory. So we just select the target board, and the target board for us is the Rev B board, and the topology will be both the encoder and decoder. From here, we click OK. And really the only thing we changed there again was for the target design, making sure that it generated an example design for the Rev B board. We didn't change any of the other functional parameters of this block. And so we can now select the block, right click and say open the example design, open the IP example design. It tells us that the modified parameters will not be available unless we save them. So we say, yeah, that's a good idea. Why don't you save that? And this is where it's going to write out the results of this exercise. And we could give it a name, otherwise it'll just give it a default name and append the current project name with the .ex for example project. So we're just going to let it do that. So that brings us to step 3-1-5. So we will click on OK, and that will start this process. And this will take a couple of moments here. The instructions actually say it will take several moments, and yeah, that's probably not a bad way to describe that. So notice this is actually invoking a second copy of the Vivado tools, and this is going to build a complete example design. And yeah, it's gonna take a moment for this to finish. That this actually could not even complete in the version 2025.1. So if you are interested in running this exercise on your own, then you would definitely need to be in the 2025.2 And that's an example where some things are supported and some things are not. But for this particular exercise, if you want to walk through these exact steps, you need to be in the 2025.2 versions of the software. So as that compiles, we will look slightly ahead in our lab steps. We're going to wait for this to finish, and we'll know that it's finished when it actually says ready in the upper right-hand corner. Once this is done, for the purpose of this exercise, we're going to go back to the previous design and just close it. We don't need that. We're not taking that forward for anything. We're not going to generate a .xsa from the previous version. We're going to generate the .xsa from the example version. By the way, as this compiled, you notice there's a little background button. If I were to click on that, then this work would go to the background, which would allow me to do other operations. I could click on other things. Right now, I'm kind of stuck, and I don't want to send this to the background because there's really nothing else for me to do until this completes. But I do have that option of, again, letting this process in the background, which means that I can click on other menu options and perform other things as long as they don't impact the current compilation. If you look at the bottom, you can see that there are lots of individual modules and individual connections that are being made. So we're actually seeing the NOC QoS designation. So you have a couple of different paths, and each one has a different assignment in terms of QoS and also bandwidth. So you see that for the most part, they just set the best effort, which that's your default until you actually go in and start making something faster or giving it higher priority, then everything comes up as a default best effort, which is not bad. That should always be your starting point. Then you selectively make certain paths faster as required or as necessary for your design. One of the things you might be able to glean at this point, if you look at the NOC view, that's being displayed while this is still processing. Notice the three little green boxes at the bottom. Those, each one of those is a DDR controller. So this particular example design, which is showing you the relationship between the video control of it, the video codec module, the processor and memory, is using three different memory connections. So that's indicated by having the three at the bottom of this. Okay, I think I am going to go ahead and move this to the background. So let it continue to generate the individual pieces of IP, and you can and let's see what we have so far. So maybe start discussing that just a little bit. So I'm going to kind of relay out the window so we can maximize this. And notice that in this example design, they're actually using five different controllers. So there are three that we could see, and when we move that box, there are another two. So again, this is an example design that you could use as a starting point. You could use it as a reference guide. You could use it as a way to learn about the tool, to be able to run simulations and do things of that nature. So if I kind of zoom into this picture, again, these are the um, DDR controllers. This is the processing system. Talk to that, and if I zoom back out, you can kind of see the overall relationship. Remember that these vertical channels actually traverse through the programmable logic. You have a horizontal knock that's along the top and then the bottom. The one at the bottom is the most heavily populated because this is where you have the processing subsystem and you have a bunch of dedicated connections from here to the knock. The ones along the top are primarily for supporting either the AI engines, which would be here if they exist on that particular device, or if you happen to be using like one of the really, really big devices, the so-called stacked silicon interconnect devices, where you have multiple die that are put onto the same substrate, then those die are connected through this NoC interface. So the NoC interface straddles from one device to the next. So that physical connection from this device, the so-called SLR superlogic region, into the next superlogic region takes place at the top. So when you use those devices, there's only a single set of processing system being utilized, but you have all the fabric and all the programmable logic resources from the other devices. And again, it's all connected through the NoC, and the NoC is connecting up top. All right, so I think I think it's finally done. So now let's move to next. So they wanted us to now go back and just simply close the previous version. So let's go to uh, project, and let's go to the original project. And we're just going to close it. Close it that way. It's not taking up memory. And again, we're not going to actually um, be using it for any purpose. So we're just going to close this project. All right, so now we're just looking at the example project. You have the NoC view that we were just examining. Then we have the diagram view. And let's come back to here. And they want us to relay out. Click on the relay out generation so that it lines up this way. And again, want to zoom in just a tiny bit, see if we can see a little bit more detail of these modules. This is the actual original block. This is the video codec unit subsystem. So they want us to click on that, expand it, kind of see what level of detail we have in here. And so you have the VCU2. You also have a knock interface. You also have a couple of other blocks that are doing control of reset and clocks. Yeah. So all this together makes for the video codec um, subsystem, which is what we were seeing at the upper level. So again, if I go back to this, so the block that I put on, but everything else in this overall example design, and again, this is an example design, involves the processing substance wizard, which just are all the details of the processor. So for instance, if I were to double click that, this would bring up the configuration window for being able to set the processor, which is very similar to what you used to do with the SIPs module, but in the newer devices, you now have a separate configuration wizard that's just for the processors. And if you look at this, you can either look at it from a graphical standpoint, or we can go to these individual menus. And you this is everything. This is how the device is going to boot. This is how you would enable PSPL interfaces, or from the processing subsystem to the NOC, the coherent mesh unit. This is how you would configure the cluster of the APUs, set up your interrupts, error messages. Basically, a lot more detail got added with this newer family. So they took the configuration wizard and they wrote it out now as a separate processing configuration wizard. It's not the SIPs module anymore. SIPs can still be used for other things, but because there's so much detail that's just specific to the processors, they now have a separate processing system wizard for that. So I'm going to just click cancel, not really changing anything here. And all they really wanted us to do was just kind of see this and then turn around and generate the device image. So we are going to, um, we could go down and actually run that generate device image. That will definitely take a longer time than what we want to expend on this, because we want to get over into the Yocto portion of this. So they kind of tell us, you probably don't really want to do that because it's going to take 2 to 3 hours for this to complete. So if you did it, then what you would then do is, after that's done, you would come to the menu, you would say File, Export Hardware, and you would walk to the menu and you would say either pre-synthesis, or if you've created a device image, then you can include that. And then that will become part of the .xsa file. So when you click on next, then you would specify what the name of the file is going to be. So it writes it as this wrapper, and then where it's going to go, and then go to next. So you get to the summary screen, and then you actually execute that. So I'm going to click cancel because I don't want to do that. So I would be at this step 4-1-5 if indeed I were exporting the hardware. And again, these are those menus that we were just looking at. So once that's done, we are pretty much done with Vivado. We have everything we need. We did the hardware configuration. We put all that information into the .xsa file. So now we're ready to either go into Vitis or go into the Yocto flow. So we can actually close Vivado at this point, and it's going to ask us, do we want to save anything? And we can say, nope. So then that gets us to the next part of this, where we're going to set up the Yocto environment. So we start off by downloading this repo tool. So we need to install this. So here I'm going to bring up a terminal window. And I'm going to now go into the software folder so I can see where I am to begin with. And from here, I can go under training. Um, then I go into the lab directory, which is this generate hardware, software, VCU. And underneath this, there is a lab and a support. So I'll go into lab software. Okay. So that's the location where I want to start um, creating the necessary steps to be able to do a Yocto build. So I'm in that location, and now I install the repo tool. So this begins by installing curl. So I'm going to say basically sudo. So I begin with just doing a sudo apt-get update. Then I want to do a install for the curl tool. All right, so having done that, and by the way, I'm walking through this, and I want you guys to understand that going forward, when you are doing, any Linux-based design, this is what you're going to be doing, unless you're still using Linux. And Linux will continue to be supported, but it's not going to be updated. And they are really kind of urging everyone to move along this path. This is what they're calling the EDF, the embedded design, the embedded development framework. Okay. So these steps that we're walking through right now are the same things that you can expect. So now we're going to install, I'm at step 5-2-3, where I want to install a couple of other utilities that are going to be run in the background. So sudo apt install. So there's just tools Z. And they tell us that these utilities are basically for doing compression, a lossless compression. And although we don't um, directly drive these tools, they get used in the background. All right. So now we want to download the repo script. And this is what AMD is actually providing for you so that you can use a specific manifest. And this is your way of accessing the specific layers and recipes that you need for AMD embedded devices. So you don't have to figure it out. You don't have to guess. You don't have to do a bunch of individual downloads. So now let's call this up. All right, so let me take one look at this command just to make sure I type it in correct. As you've already gleaned, I am a really, really bad typist, highly prone to making errors, and just basically slow as molasses. So you'll have to bear with me. That looks to be correct. Nope, screwed up something. Actually, back in our original step, we were supposed to have installed curl, the sudo app install curl. So let me click on that again.
You may have to do the apt-get update like it's recommending on the last line there.
There was an update command prior to that. So the sudo apt-get update. I had run that before,
Oh, I see.
but hey, I'm happy to do it again. So that done. Now I will do install curl. Looks like there may be some other issues here. I mean, you get used to seeing so many errors, you're not really sure which ones you actually should pay attention to. And then if I come back to this command where I'm actually using the curl utility, let me just double check my. Huh. Wow. That's a real showstopper. It's actually not even letting me getting into the more important stage of this. Is still complaining this, and this is one of the issues with working with the virtual machine is that we have to kind of go through the exact steps in the exact order that they're given to us. But if you look at instruction 5-2-2, we did both of those, and both of them seem to work just fine. There were some error messages that popped up with the app install curl, but yeah, again, if I just kind of walk back through this again, where I start with the update.
Yeah, I don't think curl is getting installed with some kind of repo. That error that you see there is preventing that, I think.
Okay. When I had run this lab before, and I'm pretty sure I did it in the same environment, I did not have these error messages. So I'm not really sure what to attribute this to, but I'm not going to waste your time as I do this. So I will need to either figure it out or consult with the customer education group and see exactly what's going on here. And what I will do is I'll walk through the complete exercise and I'll just basically post it as a video for you so you can see what the steps are. Because again, these are necessary steps for you to download repo, get the manifest, and then set up the Yocto and build environment. And that's really what I want to show you. That's the whole point of me walking through this. So I'll do that and I'll just post it as a quick video that you can take a look at. Because right now I don't know what this is complaining about, and I don't really have many options to be able to resolve it because I'm working in the virtual machine that is set up by the customer education group. This is not like me just running Ubuntu on my own machine. So with that in mind, again, I will come back to this exercise. I will walk through it. I will set it up for you to be able to view. Let me just entertain any final questions you might have, any observations, anything that you want to discuss about the Versal Gen-2 architecture, or anything that we've gone through in the presentation that you would like to get some additional clarification on before we bring this to an end. Okay. Uh, Dave, I see you unmuted. Did you have a question?
It's more of a general one, Eric. I don't know if you can answer it or not, but I've noticed that that AMD has chosen to use the AE type cores, but not the AE NOC, or sorry, CMN 600. I think that's what they've chosen to do, and it seems like the claim for ASIL D would be questionable if they don't use AE components throughout the data path. I don't know if you can comment on that or not.
Um, so first of all, help me understand when you say the AE, are you talking about the processing subsystem, or because you're not talking about the AI engine, you're talking about the
Oh,
actual.
sorry. Yeah, I jumped back to yesterday's conversation. Maybe you weren't looking for questions on that today.
No, that's fine. But I was just a little bit confused because I'm in my mind, I'm trying to link this with the AI engines, but you're actually just talking about
Just
the A78 cores, right?
just
Being
more in general, the claims for ASIL D. I
okay.
mean, I understand they've chosen the A78 AE, and that's great, but there's other parts of the data path. If you were to use them, and you have to use it, right, for to connect these cores together in the cluster, to claim it's ASIL D, it just seems like they should probably have used AE components throughout, and there is a CMN 600 AE available, I think.
So you're saying that the coherent mesh network, which is really at the top level that allows the clusters to be connected together, you're saying that that is not inherently AE certified.
Well, that's what I understood. Obviously, there's a non-AE version available, and it looks like the diagram showed it as the non-AE version. But I thought they would have picked up the AE version of that CMN 600.
Okay, unless the extent of the ASIL D is really just those two um, cores running together in that one cluster, like it's not intended to extend from one cluster to the next cluster, and that may be an inherent limitation. And if so, not surprisingly, they wouldn't exactly make a big bullet point out of that, you know, because the way that they've stated it is nonetheless correct in that if you run the two processes in lockstep, you can get the ASIL D within the cluster. They do not make any claims about being able to um, talk within multiple clusters through the coherent mesh network and have that also be uh, ASIL D. And why not? I have no idea. But you bring up a good point, and I understand exactly what you're saying. But I'm thinking that that was a trade-off that they made for whatever reasons.
Yeah, not sure. There's a whole lot more transistors in the cores than there is in the NOC, or sorry, in the CMN 600. So maybe they just assume that um, they can still meet the failure rate, like the E-8 type number, and with the non-AE CMN, and just live with it. That's I guess that's what I'm going to assume they did.
Yeah, that would be a good question for like a one like an AMD insider. I mean, somebody that's kind of really close enough to both the technology and the product marketing, because you know everything here is a decision. Everything, every level of detail, every bit of the implementation is somebody deciding, yeah, you know, this is what we want to support, and this is what we want to offer customers, and this is what we can guarantee. So, like I said, they now that you mention it, there is no there's no explicit statement that says that this is going to be ASIL level D across the clusters. So
Yeah, I don't think this is the first company to do it this way, and the CMN 600 AE may have come out later than this, than when this device was first sort of conceived. So it may just be a timing thing too.
yeah, so maybe the next generation of this product may actually have that capability.
Yeah,
So
maybe. Admittedly, I work in a different industry than automotive, so I'm just used to seeing some other automotive parts that have a full AE data path when they claim ASIL D.
right. Okay. All right. Well, thank you for that input. I appreciate it. All right. Any other questions or observations from anything that we've gone through in the training?
Uh, uh, I have a different question, not regarding the training, but regarding for the Gen 2 boot up in general. So, for the Gen 1, we can boot up from the SD card, and Gen 2 doesn't seem that to be the case. Is that a true statement? Or can we still boot up from an SD card from the, using U-boot?
Um, you can boot up from the SD card. That has not changed, and you would be using U-boot as a second stage bootloader.
Okay, so you still can boot from an SD card in the because it seems the automation I received seems like they only can boot off from the not from SD card. That's why I'm kind of puzzled.
Um, I don't think that has changed. I mean, in fact, let me let me actually go to. I'm going to bring up a slide deck that specifically talks about the boot and configuration. So
Okay.
give me just a moment. So I'm looking through this to see what if anything is different from the previous training, because the previous training was been out for years, and so I can just look at a given slide and see if there are any differences. So I'm looking. Okay, so this is what I wanted to find. Okay. So this slide deck is unique to the Gen 2 product, and this is still showing SD along with UFS, which is that's the only thing that's different here. Is now the support for the universal flash storage, but other than that, all the other options were the same ones that were being supported for. So OctoSPI, QuadSPI, eMCC, SD.
Let's see. Yeah, I do see that. Let's say the SD. Is there a different? So is there a version of Jubu for that works with the Gen 2 board?
No, it's the same. It's the same. Now you're talking about U-boot. I mean, understand that. Are you talking about using um, like U-boot and actually reading from the SD?
Yeah, so when you power up on Gen 1, you just configure one of the dip switches, and then you can boot up from the SD card, and then once then it just loads the U-boot and runs it, execute it, and then from there we configure the whatever network interface needed, and then we can actually load the OS from a network
Yeah,
TFTP to do
exactly.
it. Yeah, so so you say that should be the same. We can make to do
Yeah,
that.
yes. Should be the same. Should be the same. So basically, you indicate when you are in the boot gen process that you want to include U-boot. You configure that based on like in your case, you want to use like a PCIe interface or a network interface to be able to then load the like the Linux kernel.
Yes, or any other, the
Sure.
RTOS, you once they have to set up the TFTP and then just do the FTP over, and then just run from there.
Okay. I don't see any differences here, and if there are differences, I'm just not aware of it. But when I look at this slide, all this is, of course, about the primary boot because U-boot in and of itself is going to be a secondary boot. So, but the primary boot is where you're tying the pins high or low to tell the tool exactly which boot device you're going to use, and that choice should include SD, as shown here.
Okay, I'll look again and see that. Let's see. I say okay. Yeah, that's what I thought, but it seems like that's not the case. Okay, I'll verify again, and then okay, I'll. Okay, thank you.
Okay. All right. Do we have other issues, questions, things we want to discuss?
All
All
right.
right. So, so I'm using two different machines, so I'm getting an echo. Hold on just a moment. Okay. All right. Let's take care of that. All right. So thank you. Thank you very much for being here. You can expect a follow-up email from me with a link to this video. I will walk through this exercise again because it is important for you to understand that this is where things are headed. So for those of you that are traditionally using Pedal Linux, the sooner you understand more about this Yocto supported flow, the better. All right, so I will do that. You'll get an email, I'll have that up like within the next few days. So that's it for today. Thank you. Thank you very much for being here. I greatly appreciate your input, your attention, and hopefully I'll see you in a future training. All right.
Okay.
Have a great day.
Thank you.
Thank you, Eric. Good job.